for the opportunity to speak here. So I want to start with a quick review of Vygotsky motives. So everywhere in this talk, K will be a base field, and I will assume from the start it has characteristic 0. And lambda will be a fixed ring of coefficient.
Have you put the microphone?
Oh, I don't know. I did. Oh, okay. So should I speak louder maybe? Yeah. Okay, sorry about it. Okay, so lambda will be a ring of coefficient, and so I will, most of the time, lambda will be Q, and sometimes I will say, when I will say it, I will take lambda to be equal Z. This is just for one example that I will say later. Sorry, yeah. So dm k lambda will denote the triangulated category of Vygotsky's motives. So for this talk, it's not very important how this category is constructed. So I will skip this this part of the story. I will just give some facts about how this category behaves and some property that I hope it will give you a feeling of what this is about. It's not because that the construction is particularly difficult, but it's just I don't have enough time to somehow to tell you to give you the precise construction. So I will just give a list of properties. So I start by saying that this category dmk lambda is a lambda linear tensor triangulated category. Triangulated and it has also so it's a big one in the sense that it has infinite direct sums. Right, so I can if I have a bunch of objects here, I can take their sum. If I have a morphism, I can take its cone because it's triangulated. I can make tensor product and so on. Second property is that for every smooth K variety X, there is an object which in this category which is denoted by M of X. So it lives in the lambda, and it's called the motive of X, which is called and this is actually functorial in X. And so these motives that somehow play an important role because of the following facts. So the first thing that we need to know is that these M of X, they compactly generate, so compactly generates it's actually not completely true, so I have to twist. And so I will tell you in a moment what is this twist. It's a Tate twist, but I will define it in a moment. And what does it mean to compactly generate? This means two things. At first, these are compact, and this means that if you take maps from these objects to anything, this is an operation which commutes with direct sums. So if you think about vector space, if you are in the category of vector space, this means that the vector space here is finite dimensional. Right? If you think about it for a moment, this is exactly what it means. And generates mean that every object, so concretely it means that every object of dmk lambda is obtained from this one from the m of x's by standard operation. And I will not list this operation, but you think you know what I mean. Just operation of taking direct sums, cones, tensor product, and so on. And I maybe still need to tell you what is this state with. It's very easy to define. So, so the motive of the projective line, as you know from classical theory, decomposes into two parts, which are usually denoted like this. Right, and so these are two objects. This will be the unit for tensor product, and this is the so-called Tate motive. It's a Tate motive, pure of weight 2. And this guy, by construction, is invertible for tensor product, which enables us to define an operation like this for every n in Z just by tensoring with enough copy of this, or by its dual. Okay. So this was the second property of this category. Yeah, but it's not needed, in fact. You don't need tensors for that. And I should also say that you can also restrict to X, which is projective and smooth. You don't even need all the X's. All right. So another important property for us is the following one. So this is completely formal, but this one is not a formal property. Say the following: that there exists a fully faithful embedding from the category of Chow motive. So this is, I will not recall it, but I hope that everybody here knows what I mean by this. With coefficient in lambda, this embeds fully faithfully inside this dm k lambda. And so this embedding is somehow characterized by the following property, that it takes the motive of the Chow motive of smooth projective variety X with identity idempotent, so the diagonal of X, and this is n. It will be sent to the motive of X, which I twist by n and I shift by 2n. Okay, so this is the operation. This is this functor, and the important property is, of course, the fully faithfulness. So this is, of course, somehow gives a link between Vygotsky's category of motive and the classical category of Chow motive, which was introduced by Grothendieck. And so from the property number 2, you see that one can think about this gadget here as some triangulated envelope of this not very nice category, which has no structure except that being additive. Right? So it's a nice way to think about Chow motives, to put them somehow in this larger framework. And another property which also tells us that this category of motives somehow is related to algebraic cycle is the following property. So essentially, this is somehow everything we know about morphism in here is given by the following formula. So morphism in dm between the motive of X, so X is always smooth, so X smooth here, between X and the Tate motive, lambda n shifted by m, is given by the following formula. So it's not really a formula, it's just another name for this guy. Chow n x to n minus m lambda, and these are the so-called Bloch's higher Chow groups. So if you don't know what this means, just take m to be equal to 2n, and then you just get the usual codimension n Chow groups on X. A last property, which I will also probably not need, but just like to mention, is that it will be the opportunity to introduce a notation. So let's denote by dm gm k lambda the subcategory of dm consisting of geometric motive. Consisting of compact objects. And another name of compact object in this category is geometric motive, compact object. And I just told you what it means to be compact. This also means that an object here can be obtained again from m of x for different x's, again by usual operation, except that here we don't allow to take infinite direct sum. Right? So this is the only difference between that thing and that thing. So then the property is that every object of em gm k is strongly dualizable. And that means that, so I will give quickly the definition. This means that this is the same as saying that tensoring with the object M as an underfunctor of this category has a right adjoint of the form, again, tensoring by some other object. And then in this case, N will be called the strong dual of M. And moreover, there is a formula for the strong dual of the motive of a smooth projective variety, namely that mx. So then in this case, usually we say that n is m check, the dual of m. So the dual of m of x is again m of x, but shifted and twisted. And here d should be the pure dimension of x, if x is smooth and proper. All right, so these are the properties that list of properties that I hope is helpful to give a sense of what this. Where are you? Which line? No, that thing has a right adjoint. So what I'm saying is that this is the same as an internal home. Okay, so there's an n so that you have this equality. So a good example of, a good example to keep in mind is just a derived category of vector space. It has all these properties somehow. Of course, not that one, but somehow all the formal property are satisfied. And somehow this is a good sign because this category is supposed to be of the same nature. It's supposed to be the derived category of some Tannakian category, and this will somehow lead us to the next section. Right. So somehow, yeah, I want to introduce a big conjecture, which somehow is, I think it's somehow this central conjecture in the field of motives, at least the geometric study of motives. And so but for this I need some notation. So there is another somehow approach to motives, which is maybe slightly less known than the one I described before, which is due to Nori. Due to Nori. So here we need really to fix an embedding of our base feed into the complex numbers. And Nori has constructed a nice category. So Nori constructed. So again, I don't have the time to tell you how this construction works, but it's not because it's difficult, it's just because I don't have time. So he constructed a category, let's call it NMK, maybe with a coefficient ring, which is abelian and Tannakian even, at least if lambda is equal q, so and Tannakian. If lambda is equal to q, which is actually somehow very concrete. I mean, objects really here are just lambda modules with some structure, right? So here objects are essentially lambda modules with some action of some algebra. So lambda module plus structures, right? So somehow similar to just like mixed or structure or representation of a Galois or Galois representations. Moreover, he constructed. A comparison functor. A comparison from the category of Voivodsky motive to the derived category of NMK. So here, if I want to be more precise, I should have put maybe int Nori motives, but I will somehow not do this here. Right, so and somehow the idea is that, or at least the hope is that these two approaches are somehow the same. They give the same notion of motives. And this is actually, I mean, it's maybe difficult to explain why this is important, but let me just try to say the following things. So, so these two approaches are somehow fundamentally different because that category here is very geometric, and so somehow it has the right relation to K-theory and algebraic cycle. So the expected relation between motives and algebraic cycle somehow are satisfied in this context in the algebraic cycle. Whereas on the other hand, this category that was defined by Nori has the right categorical structure, the right and expected, of course, categorical, which means that I'm just essentially saying that this is a Tannakian category, and therefore you can use it to define a motivic Galois group and so on and so on. And somehow, what is really powerful is somehow the combination of these two facts. If you have these two facts in one context, you can prove many theorems. For example, you could prove the standard conjecture. And this is somehow why the following statement is a big conjecture. So let me give a name to that thing. So this big conjecture is saying that this functor, one has somehow to be a bit careful and restrict to geometric motives. I will maybe explain in a moment why this restriction is important. And let's just take Q. So dm with Q is an equivalence of categories between dB Nori motive. And here let me put the geometric just to say that you are looking at small things. So this is an equivalence of categories. So this statement is somehow summarize most of the conjecture on algebraic cycle and motives. I mean, but of course I'm speaking about geometric conjecture, not things related to L function and so on. It's just really somehow yes, things like the standard conjecture, vanishing conjecture in K theory, and so on. Somehow they are summarized in this statement. Sorry, I didn't define. So I somehow yeah. Nori defined this category. So he defined somehow what I'm calling here geometric Nori motifs. So these are somehow like finite dimensional Q vector space with an action of something, and that thing was like the end category of that thing. Okay, so as I said, this is a big conjecture. It seems maybe too hard to prove, and but somehow it motivates another conjecture. So which looks more approachable maybe, and this is the conservativity conjecture. Which says something weaker than that one. It says that the Betti realization, which I will explain in a moment, which goes from, so I like to denote this by B upper star and maybe a sigma to say that it depends on the choice of sigma, from dm geometric, let's just stick to Q coefficient, to d of Q is conservative. So, and let me say what mean conservative mean that B upper star sigma detects isomorphism. Right, so if you want to show that something is an isomorphism here, you just apply to it B upper star and then check that it's an isomorphism on here, which is usually a much easier task. So why does somehow follow from that? Because again, I didn't define what is a Nori motif, but I said that it is essentially a vector space with some structure. So you can forget about these structures, and then you land in dbq. And in fact, by construction, this composition is the Betti realization, which what it does, it simply takes m of x and take it to the chain complex on xc. So it maps the motif of x to the homology of this C point of x. All right, so maybe a remark. So as I said, this maybe looks much more basic and maybe simpler than that one. But in fact, my impression is that this is actually a very big step to, so the conservativity conjecture, it's maybe the main step to the previous conjecture. So mean that detects isomorphism. So if you have a map here which goes to an isomorphism by this functor, then it is an isomorphism here. Okay. Because we are in the triangulated setting, it's actually equivalent to say that an object maps to 0 if it was already 0, if and only if it was already 0. I'm not sure that I understand. So, could yeah, somehow it's not actually clear because so what is true is that on the level of the abelian category, everything can be obtained as a subquotient of some hi of some variety. But it's not clear that it's also true on the translated level. It probably is not clear. I mean, it's probably a difficult question. Sigma was the complex embedding of k into c that I fixed. It's just I wanted to stress that this functor depends on sigma. Yeah.
So the Nori motive, you have some sort of Galois representation on the tensorialization with, say, QL.
Yeah.
You're assuming that comes from a subprotein that they call homologous variety?
Yeah, it is. It is.
Okay.
Yeah.
It doesn't just assume it's like geometric.
It is. I mean, it's more than geometric. It depends what you mean by geometric, but it's really a subquotient of the homologous variety. Yeah. Yeah. It doesn't imply no, but it does not. But that one implies it, but that one not a priori. Yeah, so I want to give some remarks on the conservativity conjectures. So, I mean, there is actually I spoke here about the Betti realization, and I restricted somehow to geometric motive, but somehow you can define a Betti realization on the big category of motive. You don't need to restrict to geometric one. Of course, then you might end up with infinite dimensional vector spaces as a realization, but this is not a problem. Anyway, so then you can ask, why do I restrict to geometric motive? And it's because we have the following fact. So lemma, if the transcendence degree of k over q is infinite, then there are phantom motives, big motives, which mean that you can find non-zero object here, which will map to zero by the Betti. So it's crucial somehow to restrict to geometric motives for the conservativity conjecture. And let me give very quickly an example. So we use this condition, and so by fixing a sequence, so it's a sequence of elements in K which are algebraically independent. And then using this, you can define a motive M by taking, so it's a homotopical limit. So if you want, you can think about it as some union of Tate motives, and more precisely these guys. And so the use of this sequence is in the transition maps. Indeed, so I take the map from that thing to that thing. Next step to be just cup product with a n. So what makes this happen is that so here I'm using the fact that morphism in dm from q to q11 is given by k star. Okay, so if you have an element in k star, then you can by twisting n times you get a map from here to here, and then you take the colimit, and it's an exercise to show that it's, I mean, you need to know some facts about Milnor case theory, but one can show easily that M is non-zero. But of course, to 0 because if you think about it, so the B upper star sigma somehow commute with homotopy colimit, and then you get that B, the Betti realization of M will be the colimit of just Q shifted by N. And if you think about it as a complex, this is somehow clearly going to 0, right? So you have to use some facts about Miller case theory. Namely, I mean, what you show really is that the map, so the composition map like this, is non-zero for every n. And this is enough because this is a compact object. And the reason why this is non-zero is because it's given by the symbol A1, AN in Miller case theory. And the condition on that condition somehow implies that this is the non-zero element. You can show it by using the residue map. So this is somehow, I mean, at least for me, it's the reason why this conjecture is difficult. I mean, this is a technical reason why this conjecture is difficult is because you need to use, you need to restrict to compact motives, and this is not clear how this should be used somehow. And it's also somehow a way to check that your proof is not correct. Is you just try to show try to somehow work it out for non-compact objects, and then if it works, then it means that it doesn't work. Sorry. So right. So okay. So. But somehow I don't have an example. I don't have a counterexample to the following conjecture. This seems actually a reasonable conjecture that the upper star sigma is so from the big dm dq is conservative if the transcendence degree K over Q is finite. Somehow, all the counterexamples I know to the statement use the fact that the field is very big. Another remark is that also maybe also just a remark the conservativity conjecture is also false with integral coefficient. And here is counterexample. So here I'm working with DMC, so DMKZ. And I look at the following map. So yeah, I need to assume that, let's say, mu L, fix a prime L, and assume that mu L, mu L is inside K, and fix the generator, just a non-zero element. Well, then there is a map from Z modulo LZ as a void 0 somehow goes to Z modulo LC void 1, and so actually maps from that. So yeah, if I was in Z modulo LZ, then maps from that thing to that thing is exactly given by mu L. So I can take psi. And if you realize that thing, it's actually it's an isomorphism, right? So B of that thing is an isomorphism, but that map here is not an isomorphism, at least in the variant, the Nisnevich variant of DM. So a way somehow to solve this problem is to use étale motives. Anyway, so these were two remarks. I would like maybe to continue a little bit with the previous example and introduce. I don't know how much time I still have. Okay, so maybe I should. Yeah, maybe I will pass to some applications, some consequences of this. So. That thing here works also for, it's works for k bar. I mean, for k equals to k bar. Sorry. Yeah. The conjecture there here, it implies which one? Yeah, because I mean, DM gem is inside the big DM, so if you know it for the big one, you know it for the small one. Oh, yeah, it does, because you can always, yes. Sorry. All right, so somehow I already gave a motivation for the conservativity conjecture. Somehow it fits well with this big hope of showing of proving that the approach of Vygotsky somehow coincides with the approach of Nori, and but somehow there's also some other motivations that are actually kind of immediate consequences of the conservativity conjecture on algebraic cycle, which I would like somehow to explain now. So consequences on algebraic cycle. So maybe the most I don't know, famous consequence is the following one. So maybe let me first recall some facts. So let's assume that K is algebraically closed here. Let S be a smooth projective surface over K. Then I don't know, in the 60s maybe, I'm not sure, but Mumford realized the following, that if H0 of S omega 2 is non-zero, so if you can find a non-zero holomorphic differential to form on S, non-zero, sorry. Sorry. If this is the case, then the CH0 of X is very large. So I don't want to make it precise what it means to be very large, but in particular it means that so the natural map from the zero cycle to the Albanese of X, so if I want to be precise, I'll put K bar points, or K points here, is not injective. So if this holds, then you cannot understand the zero cycle on X in terms of an abelian variety. Right, and then Bloch somehow asked for the converse of this. And which is, so I write it because somehow there is has to make a logical effort here to maybe to understand the statement. So the Bloch conjecture, I mean, at least as I know how it's stated, so is the following. So Bloch's conjecture say that if, on the contrary, the H0 of S with omega 2 is 0, then one should have an isomorphism between CH and the Albanese point. And actually, really, the hard point is really the injectivity. So it's enough to show that the map is injective. Okay, so this is the Bloch conjecture. And so I want to explain the following, this easy maybe remark, that the conservativity conjecture implies Bloch's conjecture. so how does this work? It's so I need somehow fairly easy facts on Chow motives, or let's proof. So for every surface, for any surface, on any smooth projective surface, one has a decomposition in so Chow KQ, or equivalently in DM KQ as follow. So you can write the motive of X, of S, as so there are somehow some trivial. So S is connected, of course. So you have Q0 plus something H1 plus H2 plus H3 and plus Q2 to 4. And moreover, so of course, this decomposition somehow reflect the fact that on the Betti realization, you have so you have Q plus first homology of S, so maybe SC in degree 1, and so on. Okay, so plus H2. Okay, so this is a complex. This is a chain complex that's somehow quasi-isomorphic to that thing, and this decomposition should correspond by the Betti realization to that one. So this is somehow it's part of what is of this conjecture of called Chow-Quinid conjecture, existence of Chow-Quinid projectors. But somehow in the case of surface, it's very easy to do this. It's just using the Albanese map. It's very easy to define that thing. And so moreover, with a bit of more work, you can decompose even more the H2 of S as follow. So there is a part which somehow has to do with the Néron-Severi group of S. So again, it's with a rational coefficient, and you should twist by 1 and 2, by 2, and plus somehow the interesting part, which is called usually the transcendental part of the motive of S. So one has this kind of structure, and somehow all this is very elementary. It's really now let's go back to the case where we have moreover that so let's say if moreover the H0 0 is you get to 0. So from Hodge theory we see that so this means that the Hodge structure on H2 of S, or maybe can take homology also, is a state, right? So this condition implies that this thing is state, so it's somehow it's equal H minus 1 minus 1, right? In Hodge theoretic thing, and moreover, in this case, we have the Lefschetz Lefschetz 1-1 theorem, which tells us that this guy can be spanned. Sorry, if you intersect with the lattice, it's spanned by algebraic stack. But here the lattice is everything. So that guy here is then generated by algebraic stack. Which means exactly that it is the same as the Néron-Severi one. Okay, so what does it mean? This means that the Betti realization of the transcendental part is 0. Okay, so this is really by just using classical facts, you get that thing. And now by the conservativity, you see that this implies that the H2 transcendental of S is also 0. And now we are done because we have a formula, which also it's an easy fact, namely that the kernel of the Albanese is equal to morphism from Q0 to the transcendental part of the surface. Okay, so putting very, very classical stuff together with just this ingredient somehow implies the block conjecture. Okay, so I want to give maybe one or two other application somehow in the same vein. Again, these are only these are application on Chow motives. So another application is the following fact that lemma. So assume the conservativity conjecture, and so let X be a smooth projective variety over, for simplicity, take algebraic field, and assume that the odd cohomology groups of XC are all 0, and that the cycle map from X to H2 star XC rationalized is surjective, then the conclusion is that so give a name to this class. The class is an isomorphism, and moreover, the motive of X is state. So it decomposes completely as a sum of twist Qn to n. And the proof is really somehow kind of similar thing. So what you do, you use the fact that you take a basis. So you take a family of cycles which somehow gives the basis here, and this will give you a map from the motive of X to some direct sum of state motives. And then you know that, but when you realize, you get an isomorphism by this condition, and therefore the map was already an isomorphism, and you are done. Another application again. So this is somehow a way to construct cycles somehow, existence of cycles, is as follows. So this somehow is quite similar to the standard conjecture of Lefschetz side. So what you do again, so this is under conservativity. So let X and Y smooth projective connected of dimension D, and let gamma be a cycle X times Y correspondence, and maybe mu CH gamma. This inducing isomorphism in homology. So meaning that the map from the homology of XC to the homology of YC is an isomorphism. Okay, then the conclusion is that you should be able to find a cycle in CHD Y times X such that as you expect, so this is probably delta X and rationally equivalent delta Y. Okay. And somehow you can maybe, using the same kind of argument, you can show that if you if you know the existence of Chow-Kunit decomposition, then actually you could then the standard conjecture of Lefschetz type is also true by the same argument. All right, so I think my time is up, so I finish here.